Okay, so for this problem, what we're going to look at, the first thing that this says is the volume of a sample of gas is 2 liters. So this is going to be my V1 when the temperature is 11 degrees C. This right here is T1. While the pressure remains constant, the temperature, so pressure remains constant, so we need to not worry about pressure, so we're not going to change anything with pressure. Temperature is changed to a new value, so we are looking for a new temperature, so we have P1, which equals, sorry, scratch that. We have V1, which equals 2 liters. We have T1, which equals 11 degrees Celsius plus 273. And we have V2, which is 3 liters, which it says right here, right? And we need to find T2. So that's what we're looking for. So in this case, the formula we're going to use is V1 over T1 equals V2 over T2. We're going to cross multiply, so V1 T2 equals V2 T1, and we want to solve for T2, so we want to divide both sides by V1. Okay, so in that case we end up with, let me erase this here, we're going to go ahead and fill everything in. So we now know that we have what? So cancel, so we have T2 equals V2, which is 3 liters, times T1, which is 273 plus 11, so that's going to give us 284 over V2, which is 2. And so my answer, when I plug all this into the calculator, is 426. And since we are dealing with temperature, right, so we have temperature, my units are going to be Kelvin, because remember we changed this to Kelvin by adding 273. Alright, next problem here. So this one says that we have the volume occupied by a sample of gas is 480 milliliters, so this is my V1, right? When the pressure, so this is my P1, sorry, that's a 1. What pressure, okay, must be applied to the gas to make its volume become 650 milliliters? So this is my V2, which means I am looking for P2. This is what we're trying to find, right? So we want to use P1 V1 equals P2 V2. How do I know I'm going to use that formula? Because all I've been given are pressures and volumes. I wasn't given anything else, okay? So, alright, so now we need to find, since we're looking for P2 in this case, and the reason I know we're looking for P2 is because we have P1, we have V1, we have V2. So then we want to divide both sides. So we're looking for P2, right? So we want to divide both sides by V2 so that V2 cancels out. So that my formula now becomes P2 equals P1 V1 over V2. We're going to plug our numbers in. So we have 115 times, in this case, 480 divided by 650. And the answer that I'm going to get is 85. I rounded, it was 84.9. And in this case, we're dealing with pressure, right? So we're looking for the pressure here. And since these units were kPa, then I want to do kPa down here. So kPa are my units, and this is an example of Boyle's law. Alright, next one we got, this one jumps to station 5, so we're a little bit out of order, but that's alright. Alright, so for this one it says the volume occupied by a sample of gas, so volume, this is my V1, okay? When the pressure is, this is my P1, okay? And I know that because my units are ATMs. What volume? So we're looking for another volume, so over here we are looking for V2, okay? At a constant temperature, which means we do not worry about temperature. So if we only have pressures and volumes, this again is an example of Boyle's law. Okay, Will the gas occupy when the pressure decreases? So my pressure is going down, and we're going to have our second pressure. This is my P2. So same formula. P1 V1 equals P2 V2. Okay, we are looking for V2, so I'm going to divide by P2. Okay, so that my new formula becomes V2 equals P1 V1 over P2. Let's plug everything in. So in this case, we get 1.2 times 2.4 divided by 0.86. And my answer is we're going to go with 3.3, okay? And, well, actually 3.35 because of sig figs. And my units are going to end up being liters because, remember, we're looking for volume, and my other volume was in liters. All right, station 6, it says, when a sample of gas, let's see, the volume of sample gas is 2.5 liters when the temperature is 270 K. So in this case, temperature is already given to us in Kelvin. This is my T1. We don't have to change anything. This is my V1. Remember, it's liters. If the temperature is changed to 30 degrees C, so 30 degrees C, what we're going to do, this is going to be my T2, okay? And so we're going to take 30 plus my 273, this degrees C. We are going to get 303 K. So that's my T2. What will the new volume be? So we are looking at V1 over T1 equals V2 over T2. And again, we're looking for V2. That's what we don't have. So in this case, let's cross multiply. V2, T1, which you guys can see we're going to take these and these, right? So V2, T1 equals V1, T2. All right, and so now we're going to go ahead and we're going to divide by T1. Divide by T1 since we are looking for V2. And so these are going to cancel here. So let's go ahead and plug our values in. So my V1 was 2.5. And I'm going to multiply that by my T2, which was 303. And I'm going to divide that by my T1, which was 270. And the answer that I'm going to get, I'm going to move this up here. So my answer is, we get a whopping 2.80. And since, what are we looking for? We're looking for volume. These units should be liters, okay? And so this is an example of, since we just have volume and temperature, this is Charles' law. Okay, in this problem, we want to determine the pressure change when a constant volume, so we're not going to worry about volume, of gas at 1 atm, so this is my P1, is heated from 20 degrees C, so this is my T1, to 30 degrees C, which is my T2. In this case, since we're only dealing with pressure and temperature, we are talking about Gay-Lussac's law. And in this case, we are looking for P2. We know the formula is P1 over T1 equals P2 over T2. Let's go ahead and cross multiply so that we end up with P1 T2 equals P2 T1. We are looking for P2, so we're going to divide both sides by T1. And so in this case, my formula is going to end up being, cancel these out, so P2 equals my P1 T2 over T1. So now I'm going to go ahead and plug these values in. So in this case, pressure 1 was 1 atm times my temperature 2, which is 30 degrees C plus 273, which is going to give me 303. So we're going to say 1 times 303 over, in this case, my T1 is going to be 20 degrees plus 273. All right, so this is going to give me over 293. And my answer is, go ahead. So it's going to be 1.03. And since we're looking for pressure, and these units are in ATMs. Here, my units are ATMs. All right, so on this next problem here, we're going to look at if a gas is cooled from T1, which is 323 Kelvin, to my second temperature, which is 273, and the volume is kept constant, so we are not worried about volume. What is the final pressure would result if the original pressure was, so this is my P1. All right, so in this case, we're looking at pressures and temperatures. So again, this is Gay-Lussac's law. And we're going to set this up. P1 over T1 equals.
Yes.
Sorry, Dylan. What's Dylan's last name? Palma. Anyway, he so rudely interrupted me.
Can I read it too?
All right. So in this case, sorry, I'm trying to get my pencil to work. This equals, just scribble that out. P2 over T2. All right. So we're going to cross multiply. P2 T1 equals P1 T2. In this case, we are looking for P2, so divide by T1, divide by T1, cancel, cancel, and let's fill these in. So P1 we said was 750 times my T2, which is 273.15, divided by T1, which was 323. So my answer will end up being, and remember, millimeters mercury is a unit of pressure, K, unit of temperature. All right, and so your answer here should have been 634, and again, we are looking for pressure, and so my units, since these units were millimeters mercury, my units here will be millimeters Hg, which is millimeters mercury. All right, so in this problem here, we're going to look at it. It says a child has a toy balloon with a volume of 1.8 liters, so this is my V1, and a temperature which was 20 degrees C, so this is my T1, and a pressure of 1 atm, this is my P1. If the child were to let the balloon go and it rose 3 kilometers, so we don't really care about that, that's information, it's just telling you how high it's going to go, and the pressure is 0.67 atms, this is my pressure 2, and this is my T2. Okay, so what would the new volume, so we are looking for V2, this is what we are trying to find. So in this case, we're looking at pressure, temperature, and volume, so this is my combined gas law. That's the one we're looking at here. Okay, so we said we're going to use the combined gas law, so remember combined gas law is P1V1 over T1 equals P2V2 over T2. In this case, we're looking for V2. So the first thing that I want to do is to cross multiply. So we're going to cross multiply these here so that what I end up with is P1 V1 T2 equals P2 V2 T1. Okay, and we're trying to get V2 by itself, so we're going to go ahead and divide by P2 T1, divide by P2 T1, and I'm going to cancel out my P2 T1, P2 T1, so that what I'm left with is V2 equals what we see there. So let's go ahead and plug in the values for this. So V2 equals my P1, which was 1 atm, times my volume 1, which was 1.8, those are 8, times my temperature, and remember you got to convert that to Kelvin. So in this case, we're going to take our negative 10 here, plus my 273, which is going to equal 263. And I'm going to divide that, keep everything in top in parentheses, and put it in everything on bottom in parentheses. So in this case, this is going to be 293, because again, it was 20 degrees C, and we added 273 to it. And this is times, what else are we looking at? P2, and P2 was 0.667.
But this, like these two.
Hold on, what was that answer?
Years.
I think the answer we just got was 2.42, and in this case, since we're looking for volume, this would be liters.
I'm sorry, Dr. H's class. I erased it.
All right, next problem here is this is station 8. So this says calculate the pressure. So we see that we're looking for pressure. That's what the question mark is. We are given 0.42 moles. This equals N. Helium gas, 2.54 K. This is my temperature. And it gives me my volume, which is 3.32 liters. So we're going to use PIVNERT. PV equals nRT. And again, in this case, we're looking for pressure, so we want to divide both sides by V, so that what we end up with, V and V cancel out, sorry. So we get 0.421 moles times, and remember R is given to us, right? So R is always going to be the same thing. So R is 0.0821 times, what's our temperature? 254. Divided by, and make sure you keep that in parentheses, divided by my volume, which is 3.32. Alright, so my answer here was 2.64, and again, since we were looking for pressure, my gas constant, the one that I gave you, this one here, by apprentice, that the pressure is in ATM, so that would be our pressure. Station 9, this is exciting. We're getting close to the end. Okay, so we have 3.25 liters. Liters tells me that this is a volume. Of ammonia exerts a pressure. So here we go. Here's P. I have my temperature, T. And since they didn't give me 2 P's, 2 V's, 2 T, any of that kind of stuff, we know that here we're going to use the ideal gas law. So we're going to have, again, PV equals nRT. In this case, we're looking for moles, so let's divide both sides by RT. Divided by RT. RT cancels out, so that we have, my formula is PV over RT equals N, right? So let's substitute some things in. My pressure is what? 0.652 times the volume, which we said was 3.25. Divided by parentheses 0.0821. Okay, and our temperature value we had in there was, we're going to multiply this by 243. Make sure when you put this in the calculator, leave everything on top in parentheses, and then divide by everything that's on bottom and keep those in parentheses separate, or you will get the wrong answer. So the answer here is, so we get a 0.106. And since we're looking for moles, then you would just say that these are moles. Alright, last one of these more in-depth problems. Toy balloon has an internal pressure of 1.05 ATMs and a volume of 5 liters, okay? If the temperature where the balloon is released is 20 degrees C. So right here we're talking about, this is my P1, this is my V1, here is T1, and remember we've got to add 273 to that. What will be the volume when the balloon rises to an altitude where the pressure, so here's P2, and the temperature, T2. So what this means is that we are looking for V2, is what we don't have. So let's go to our ideal gas law. P1 over V1 over T1 equals P2, T2 over, this should be V2, this should be a T. Okay, so let's cross multiply, then divide. So I want P1, V1, T2 equals P2, V2, T1. And what do we say we want by ourselves? We want V2. So we're going to divide both sides here by P2, T1 divided by P2, T1, which means that now I have V2 by itself. So let's go ahead and erase these other guys here. All right. Say goodbye. Alright, so that's our problem so far. Let's go with, then let's plug in some values. So my P1 we said was 1.05, right? Times, what else do we have there? That's ugly. Let me erase this. Okay, let's start again. Alright, so we have 1.05. That's my P1. What was my V1? That was 5 liters. Alright, so we got 5 liters here times 293, and remember 293 comes from, we've got 20 degrees C plus 273, and we're going to divide this by P2 times T1. P2 0.65 times, now remember my T2, we're going to take my negative 15 plus 273, so this number is going to be less than 273, right? So we get times 258, and what do we get for an answer? Alright, and so here we're going to get an answer of 9.17, and my units over here, since we are looking for volume, is going to be liters. And this is an example of combined, and the reason it's combined is because we are using pressure, volume, and temperature. Alright, so this problem here says that we are going to draw arrows to represent how molecules create pressure inside and outside of the balloon, okay? So this one's pretty simple, right? So we've got molecules that are inside, and they're going to move around, and they're going to push out on the balloon, right? And then here we've got molecules on the outside, and they're pushing on the outside of the balloon, creating that pressure there. So when we put this gas in the bell jar, if you guys remembered that, what I want you to think about is when we took out the pressure that was on the inside, so if I took out the pressure that was on the inside, which were these, right? Because I can't, the inside of the balloon was sealed, but on the inside of the bell jar, right? When I take these out, what happens is now my balloon, these molecules inside here, they're going to push out harder. And so with more force, because they have nothing pushing in on it, and the balloon will actually end up getting bigger. So remember, this goes back to our pressure, volume, temperature. In this case, what were we holding constant? We were holding constant the temperature. So this should be a T here, and this should have been a V. All right, hopefully that looks all right. This should be a V here. So we were keeping the temperature constant. So what we saw was this. When we decreased the pressure, we saw that the volume was going to increase. Alright, here, if the pressure is increased on a balloon and the temperature is constant, okay, so since the temperature is constant, we're not going to worry about it, alright, what happens to the volume? So again, let's look at our little handy-dandy stick thing here. So this was P, T, V, okay, and we said the temperature is constant, so we're going to get rid of that temperature. Alright, the pressure increased, so my pressure is going to go up, which means that my volume has to go down, right? So this was the bell jar example, which I just kind of talked about in this other one. So what we would see is the pressure went up and the balloon would get smaller. And you guys know this, if you sit on the balloon, the volume of it has to increase the pressure. Alright, so in this problem here, this isn't that much different than one of the first ones we looked at. So what do you think would happen if we increased the temperature? So in this case, we're saying that the pressure is constant, so we're not going to change the pressure. So what that's going to look like is this. If I've got 4 molecules inside, well, I'm just going to go draw 3 because I'm being lazy. Then that means I've got 3 on the outside, okay? So we're not going to change the pressure that's pushing on the balloon. But what we're going to do is we're going to make these ones on the inside, we're going to make these molecules in here hotter. And so what happens is when they're hotter, they're going to move faster and they're going to hit the walls of this container harder. And so what happens is that your balloon is now actually going to increase in size, okay, because they're hitting the collisions are harder against the walls of the container. So this goes back to our PTV, right? And we said that we're going to hold the pressure constant, so this means that as the temperature increases, the volume has to increase as well. The volume has to go up. Alright, here we go. Explain what is happening in the picture as the piston moves in each example. So if we look at this first one, we can see that from here to here, this is my volume 1, right? So from here to here, this is volume 2. And it looks like the volume here increased, right? Well, and it also looks like this piston that we have here isn't being pushed down as far. So we would say that the pressure then decreased. On this other side here, it looks like the piston has moved down further, so we had to increase the pressure. So the pressure increased, and then this picture right here shows you that the volume decreased, okay? So in this one, the molecules are closer, which equals more pressure. Okay? Over here, we would say that the molecules are farther apart. And you guys can figure that out. If it's farther, did I spell it right? Farther apart. If they're farther apart, then less collisions, less pressure. All right, last problems that we're going to do. The units we need to look at. All right, so pressure is going to be in millimeters mercury, torr, ATMs, and kPa. Temperature, we know Kelvin, we know degrees Celsius, and we know degrees Fahrenheit. Remember, if you guys want Kelvin, it is 273 plus my degrees Celsius. And volume, we're going to see this in liters, milliliters, and sometimes centimeters cubed. I feel confident that you guys are going to do well on this test. You're going to finish out this year with high grades, better than you've done the rest of this school year, just because you are focused and ready to go. Good luck on your test.